Started. Yes, we are broadcasting. Okay. So arc length is easy in some way and hard in others. So arc length. And we came up with a formula for it the other day. It's the integral, if I'm using a function of x, as x goes from something like a to something like b, of the square root of 1 plus f prime squared. And there's a similar version, pretty much identical, switch x's and y's if you're going the other direction. And this is just a direct consequence of Pythagorean theorem and a Riemann sum. And we looked at that the other day. The complicated part here is for a lot of elementary functions, this integrand is just going to be impossible to find an antiderivative for. And we have to resort to using some numerical techniques, usually a computer program. Okay. Every once in a while, there are some special curves for which this cleans up nice. One of those special kinds of curves is called an asteroid. Not an asteroid, but an asteroid. Asteroid means star-like. And so, let's switch colors to black. And so this is problem number 11 in the book. And an asteroid has the general shape of a 4-pointed star. So let's say that, we'll call that A, negative A, and negative A down there. And the asteroid looks something like this. It has 4 symmetrical pieces. And that point is supposed to be on the axis there, but my pen was a little off. So this is supposed to be perfectly symmetric here. And the asteroid equation is x to the power 2/3 plus y to the power 2/3 equals a to the power 2/3 is the equation of an asteroid. If we solve that for y, then we'll get y equals a to the 2/3 minus x to the 2/3 all to the power 3/2. And here we're essentially taking the square root of a square over here when we do that. So there's some pluses and minuses going on. So when we solve for y, we don't get all of it, because clearly this red thing is not a function, right? Yeah. So it's a little more complicated than that. And so what we can do to find the arc length is we can use some symmetry of this figure. And so what we'll do is we'll just cut this figure in half, and we'll just look at half of that segment in the first quadrant. So once we find that length, we'll multiply it by 8 to get the whole thing. And some of you may have already tried this one in the homework. And your homework question, maybe A was 2 or 3 or 5 or 7. The computer threw in different numbers. The version in the book, A is 1. Okay, but that's the general version of it. So we're going to try to do that now. So remember, we have 5 steps to find arc length. We break this down in terms of finding the derivative, squaring the derivative, adding 1, take the square root, and then see if we can find an antiderivative. Okay, so I'm just going to break this down in terms of those 5 steps based on this black version of the equation y equals. All right. So step 1 is to find the derivative of that black function, which is going to involve the chain rule. So new page. So remember, y is equal to parentheses a to the 2. Oh, and actually, let's pick a problem. Let's pick a number for a instead of using a. This one that it gave me had a 7 in it. I remember seeing Darren's yours had a 5 in it. Yeah, so it's pretty similar for everything. So I'm going to replace a with 7. So I'm going to have 7 to the power 2/3 minus x to the power 2/3, all to the power 3/2. And remember, you can't distribute a power over a sum or a difference. Doesn't work. So I can't clean this up yet. I have to take the derivative. So y prime here is going to be 3/2 times this. And we just had someone join us Who do we have there? That looks like a classroom somewhere else in the world. Samantha, perhaps, or Stanton? Hello? Hello out there. Could you mute your mic until you need to talk? All right, we'll try again in a minute. They walked away. So we've got 7 to the 2/3.
Are you on the video?
Minus x to the 2/3. And then we reduce the power, so we get 1/2. Hello, who do we got there? Is that Sam?
Yeah.
Hi, Sam. Can you mute the mic until you need to ask a question? Otherwise, it interferes with the recording.
Yep, will do.
Thank you. And we're taking a look at problem number 11 in the book, or in your homework, excuse me, the asteroid problem.
Okay.
So again, this is number 11. All right, so y prime, let's see, I'm partway there. Derivative of the inside from the chain rule is going to be what? Negative x to the power negative 1/3 times 2/3. Does that look right? And that cleans up a little bit. So what do we have? The 3/2 and the 2/3 will cancel. So I'll have a negative x to the negative 1/3 times 7 to the 2/3 minus x to the 2/3, all to the, that's supposed to be a 1/3 up there. Oh, wait a minute. Is that, no, it's supposed to be 1/2. I had it right the first time. Oops. That is a 1/2 to the power of 1/2. Okay, so this is what I called step 1. Step 2 is to square that sucker. What is y prime squared? Well, we can distribute a square over multiplication here. So the square of negative x to the 3/2 is positive x, sorry, to the negative 1/3 would be positive x to the negative 2/3. And then the square of the square root here is just going to be the parentheses, 7 to the 2/3 minus x to the 2/3. So that's the square of my cleaned up y prime. So a lot of these problems are algebra intensive. Here I can distribute now because I don't have a power up there anymore. Good question. So if I take negative x to the negative 1/3 and square it, the negative 1 out front, that's a negative 1 out front. Negative 1 squared is positive 1. And then a power to a power is multiply the powers. So that's where I get the x to the negative 2/3. Okay. Yeah, ask questions, please, if I do something that you think is screwy. All right, let's move that out of the way. Okay, so distributing here, what do we get? We're going to get a 7 to the 2/3. Oops, I wanted to write in blue. Oh well. Times x to the negative 2/3, and then x to the negative 2/3 times x to the positive 2/3. What's that end up being? That's just 1, right? Because that'll give me x to the power 0, which is 1. So I'm going to have a minus 1 there. Now, I'm really excited about that minus 1 because the next step is to add 1, right? So that's cool. So step 3, new page, is to take, so step 3, 1 plus y prime squared. So that means I have 1 plus that 7 to the 2/3 times x to the negative 2/3 minus 1. So plus 1 minus 1 goes away. And this cleans up to be just 7 to the 2/3 times x to the negative 2/3. And I'm ready to take the square root of that. So step 4 is the square root of 1 plus y prime squared, which means I have to take the square root of that 7 to the 2/3 x to the negative 2/3. And that's kind of cool because the square root is what power? The 1/2 power. So now I have this thing to the 1/2. And so that's going to give me 7 to the 2/3 to the 1/2 times x to the negative 2/3 to the 1/2, because we can distribute powers over multiplication. So here we're getting like the most intensive power, exponent rule review ever, because we can use every rule there is. And this is kind of nice because 2/3 times 1/2 is 1/3. And negative 2/3 times 1/2 is negative 1/3. So this cleans up pretty nice. 7 to the 1/3 times x to the negative 1/3. How we doing? Not too bad? Isn't this exciting, all this canceling stuff? And that's my integrand, right? That's the next step, to integrate that sucker. All right, so I want to integrate 7 to the 1/3 times x to the negative 1/3 with respect to x. And in the problem, they gave me the boundaries of integration. And it's kind of this works in general for any asteroid. The x and y value for that midpoint here, this number right there or there, is going to be x equals a times the square root of 2 over 4 all the time. So if your a was 5 on the homework, then they said integrate from 5 square root of 2 over 4. If your a was 7, they said integrate from 7 square root of 2 over 4. So I'm just going to double check I'm not a liar by looking at the problem. And yeah, it says 7 square root of 2 over 4 to 7, which is my value for a on the right side there. All right, back to that page. So here I want to make a note. X is going to go from 7 square root of 2 over 4 to 7. Let's see, antiderivative for this thing. The 7 to the 1/3 is just chilling out. It's a constant. And then let's see what happens with that. I'm going to add 1 to negative 1/3, which is going to give me 2/3. So I'm going to have an x to the 2/3 divided by 2/3, which is the same as multiplying by 3/2. Right? So that's one version of the antiderivative. And x is going from 7 square root of 2 over 4 to 7. And plugging in the lower bound is about as hard as the algebra we did earlier. So we're gonna have to clean that up quite a bit, but it cleans up nice. All right, so I have an antiderivative. Doesn't clean up too much. I think I'm just gonna leave it the way it is and start plugging in numbers. So let's see. Plugging in the top boundary, I'm gonna get 7 to the 1/3 times 7 to the 2/3. Ooh, that's nice, isn't it? Times 2/3. Oh, 3/2. Oops, upside down. Minus 7 to the 1/3 times parentheses 7 square root of 2 over 4 to the power 2/3. All right, times 3/2. And it looks like quite a mess, but we have some things on our side here, right? The 7 to the 1/3 times 7 to the 2/3, what's that going to be? 7 to 3/3 or just 7, right? So this is just going to be a 7. Well, here's a 7 to the 1/3, right? And there's a 7 to the 2/3 over here too. So that's going to clean up a little bit. But then I have to clean up that part right there. So I'm just going to scribble off to the side for that. I just want to think about square root of 2 over 4 for a second. Square root of 2 over 4 could be rewritten as 2 to the 1/2 over 2 squared, right? And if I do that, that means my power is going to be 2 to the 1/2 minus 2. Well, 2 minus 1/2 would be 3/2, so that must be 2 to the negative 3/2. And then I'm raising that sucker to the power 2/3. Okay, so I'm going to rewrite this on another page. Hopefully I'll get it correct. So new page. So I've got my 7 to the 1/3, 7 to the 2/3. That's a 1 times 3/2. So that leading part is just 3/2, right? Yeah. And then in the next part, I'm going to have 7 to the 1/3 times 7 to the 2/3. And then my claim is that square root of 2/4 is really 2 to the negative 3/2. So then I have a 2 to the negative 3/2 to the power 2/3. And, oops, wrong button. And I still have that 3/2 hanging out front. And things here clean up quite nice. We know that guy right there is just, ooh, I did something wrong. This should have been a 7 out front, shouldn't it? Okay, thank you. I don't know why I said it was a 1. It was 7 to the power 1. I was close. All right, so this guy right here is just a 7, right? And then here, let's see, what's that? That's 2 to the negative 3/2 times 2 to the to the power 2/3. 3 negative 3/2 times 2/3 is -1, right? So essentially this guy right here is 1/2. And I also have that 3/2 there. So it looks like, and I still have the 7 times 3/2. So what's that? 21 halves minus 21 fourths. Doubling top and bottom of this one. 42 minus 21 is 21. So it looks like the answer for 1/8 of our graph's arc length is 21 fourths. Just a note that 21 fourths could be written as 3/4 times 7. Is there anything special about the number 7? That's our A here. Yeah, so in general, it turns out 1/8 of the figure is going to be 3/4 of whatever A is. Yeah, it just works out that way. Now, we really want 8 times this. So 8 times 3/4 of 7. 4 goes into 8 twice. 2 times 3 is 6. So in general, it looks like the whole arc length of the asteroid is going to be 6 times whatever A is. So in our case, it's 42. And I think, Darren, do you remember when your A was 5, did you get 6 times 5 or 30 as the answer? Yeah. Yeah, so in general, it looks like, going back here, we have a conjecture that the arc length of an asteroid is 6A in general. Okay. So if you haven't done this problem yet, you could just go in now and try plugging in whatever 6A is, but I highly suggest you practice that algebra again, just to review the crazy power rules all mixed up together here. All right, let's see if we can get a fantastic out of the computer. And so, oh, I already did this one, 42, right. Okay, let's do a similar question. Similar question, they give me a radius of 4. So what do we think the arc length of the entire thing is going to be? 24. So let's see, 24. Check answer. Well done. Okay. Cool. That was so much fun. Hi, Stanton.
Hi. Could you do number 9?
I certainly can try. Number 9. Okay. Use a grapher or computer to find the length of the curve numerically. And so we have y² plus y equals x plus 5. And then they give us points to look at. Okay. So this is a sideways parabola. And let's copy that into my notebook. Okay. So first thing we should do is visualize the graph. So we need some kind of computer to do so. If you have a TI and you can't graph X as a function of Y, you get a couple of different options. You can, for example, solve for Y here, in which case you'd probably have to whip out the quadratic formula and you'd have a funky square root function that you could graph half at a time. GeoGebra is able to graph the whole thing. So I'm gonna jump to GeoGebra. You could just graph, switch the X's and the Y's and switch the points, and that totally works too. So you got a couple different options on how to proceed there. So I'm gonna go for the version they gave. I don't want my unsaved changes, probably y squared, was it plus y equals x plus 5? Would be that one right there. And then they said to use the points. Was it 5, -1? Where'd you go? Here. -5, -1, and 7, 3. So -5, comma, -1, and 7, 3. All right, let's move it so we can see. Move. All right, so we're trying to find this particular arc length right there. And the problem with trying to solve this for X is we'd have to break it into 2 portions. With Y, we don't have to do that. GeoGebra gives me this quick utility of making a line segment in between, and then I can ask for the length, come on, of that line segment. Oh, there we go. Object properties, show name and value. So the line segment in between is 12.65, so I know my arc length's got to be bigger than that. So we get a rough guess for that. Okay. So where's my notebook? Right there. All right, let's do it. So here I want to rewrite this, oops, X as a function of Y. So I'm going to call this, oops, where's my pen? Black. X in this case would equal Y squared plus Y minus 5. And so same steps apply as before. First, I have to find X prime. So that's going to be 2y plus 1. Second step, I square it. So 2y plus 1 squared is going to be what? 4y squared plus 4y plus 1. When we multiply it by itself. Step 3, add 1 to that squared derivative. Well, that's not too bad. Y squared plus 4y plus 2. Step 4, take the square root of that whole thing. Now, just note here, I did have a perfect square until I added 1 to it, so it's no longer a perfect square, which means I can't clean up the square root. I could complete the square on it, and if I did that, it would take me back to this thing plus 1. That doesn't help either. Okay. So at the moment, the only thing I have in my tool belt is to say, somehow I need to take the integral as y goes from, what was it, -1 to 3 of that square root function. And at this point in my notes from yesterday, I said we have 2 options. Pray we can find an antiderivative, or try numerical integration. And the computer said, use a computer to try and find the answer here. Okay. There may be a way in chapter 7 to do this, but we don't have a technique to find an antiderivative right now. Okay. Any u substitutions we throw on it with what we know right now aren't going to lead anywhere. Right. If I let the u be the whole thing inside here, inside the square root, then du is going to have to be what? 8y plus 4, which doesn't live outside of the square root. So I have a problem either way. So now we just whip out some program to do this. If you were doing this on a TI, TI lets you choose your variable of integration. So you could still use y's on the TI, or we could just ask GeoGebra to do it. I'm going to rewrite it as x's. GeoGebra wants x's when it does it. So yeah, it's going to be the same length. Yeah, so it doesn't matter. So I'm going to go int function start value end value. My function is that square root function. So I have to type sqrt, oops, don't need parentheses, of, what was it, 4, and I have to do an x squared plus 4x plus 2. So that's my function that I'm integrating across, and I'm doing it, tab, from -1 to 3, is that right? Yep, -1 to 3. Now it's going to draw a picture of what it thinks it's doing, which doesn't relate to what I'm doing. And I get an answer of 13.61 for that arc length to 2 decimal places. I can't remember how many decimal places they asked me for. To the nearest hundredth, yeah, so GeoGebra gave it to me to the nearest hundredth. So according to GeoGebra, where'd you go, GeoGebra? There you are. It's 13.61, excuse me. And let me blow that up. Where's that? Options, font size, 24 is usually nice. Come here. There we go. So the 12.65 was the distance directly between the points. We knew had to be bigger than that, and it turns out the actual length of the arc here is 13.61. Okay, so let's see if it works just for fun. 13.61. Nice work. All right. Okay, so I think the asteroid was probably the hardest one. Oh, here we got to do a little trigonometric. Oh, let's see, what do they want here? Let's do this one since it's here. Let's see. Find the length of the curve, and they want us to choose the correct answer for the integral. It looks like the correct one is A. Oh, no, wait. No, the correct answer is D. How do I know that? Well, let's figure it out. No, I didn't check anything, so it's going to be 1 plus something, unless but we got to be careful. Like trigonometric identities, crazy stuff happens, right? So we better write something down just to be safe. So my guess is it's D just by looking at it. So let's bring up a new page here. All right. So I'm going to take a screenshot of the given information and see what happens. All right. So so here they're defining my function as an integral, and integrals can be functions, right? Even if I can't find an antiderivative, it can still exist and be a function, as long as the function, the integrand, is mostly continuous. And the square root of cosine of 2t is totally continuous from 0 to pi over 4. I can guarantee you that. All right, so first step is to find y prime. Well, that would be the derivative with respect to x of that integral as x goes from 0, oops, dummy variable t, sorry. As t goes from 0 to x of the square root of the cosine of 2t dt. Now, what rule allows me to clean up that mess? The fundamental theorem of calculus says, hey, these guys cancel each other. So this is just going to be equal to the inner function, which is the square root of the cosine of 2x. I have to evaluate it at the endpoint. The constant endpoint disappears because we're taking the derivative of a constant. That plus c is gone. And then the chain rule says you have to take the derivative of x with respect to x, which is 1. Nothing happens there. I always like to double check that one. So that right there is y prime. All right, what was step 2? Square it, right? Y prime squared. Okay, I love that. That's just the cosine of 2x. Step 3, add 1. Okay, 1 plus the cosine of 2x. Step 4, take the square root. All right, well, that's the square root of 1 plus the cosine of 2x. Oops, where's my x? And then I can put it in an integral. And so the arc length that I want is going to be equal to the integral as x goes from, I think it was 0 to pi over 4 of the square root of 1 plus the cosine of 2x with respect to x. And I'm pretty sure that's what d was. Next question. Can we find an antiderivative, or do we have to resort to a computer? So let's see, I'm just going to pick D and see what they asked me to do next. Okay. All right. Now they want us to find the length of the curve. Notice they do not say with a computer. So the implication is I can find an antiderivative. So trigonometric identities, does that look like something you've seen before? Like think of double angle versus half angle formulas. So I'm just going to look up trig identities here. And I think we should find that. Here's a SOS Math, I think has a good one. Where are you? Double angle. Okay. Check it out. 1 plus the cosine of 2u is equal to, if I multiply the 2 to the other side, 2 cosine squared. Let me blow that up. Yeah, this guy right here. That's the inside of my square root, right? The top, put the 2 on the other side. So we have an identity that says this is equal to the integral of the square root of 2 cosine squared of x. Oops, pi over 4, sorry. Dx. No, the 2x is right here. Yeah, so check back on the formula. Formula says the cosine squared is equal to 1 plus the cosine of 2u over 2. Now, I didn't have the over 2, so I'm multiplying that 2 up to the other side. Yeah, so 1 plus the cosine of 2u is twice the cosine squared of u, which I think is what I wrote here. So where's my highlighter? So 1 plus the cosine of 2x should be equal to twice the cosine squared of x, according to that identity, which is nice because square and the square root do wonderful things together. So now I have the integral as x goes from 0 to pi over 4 of the square root of 2 times the, technically that's the absolute value of the cosine of x, because the square on the inside eliminates signs and the square root only puts out non-negative answers. All right, so let's think about the graph of the cosine before we proceed, because we might have problems with SIGNs, positives and negatives. Let's see, the cosine, peaks at the axis at 1, and then it drops down and then rises up again. So let's see, it rises up again at 2 pi. So this right here would be at x equals pi. That 0 right there is at pi over 2. So pi over 4 is about right here. Cosine's positive in that region. So I don't need to worry about the absolute value. Otherwise, if I did, like if we were trying to go all the way to pi over there, I would have to break this into 2 integrals or use symmetry to do it, right? So we got to be careful, but we're okay here. What's an antiderivative for cosine of x? Sine, because the derivative of the sine is the negative cosine, isn't it? So yeah, I know, just so antiderivative is, you're saying it's the sine? Okay, but what's the derivative? Oh, derivative of the sine is the positive cosine. Okay, yeah, you're right. I was screwing up there. Thank you. So antiderivative here is just the sine. We have the square root of 2 hanging out. I'll put that out here. Sine of x from 0 to pi over 4 And the sine of pi over 4 is what? Square root of 2 over 2? Is that right? So I'm going to get square root of 2 times sine of pi over 4 minus the sine of 0. Oops, parenthesis. Sine of 0 is 0, isn't it? Yeah, so it looks like this is just square root of 2 times the square root of 2 over 2. Square root of 2 times square root of 2 is 2. Over 2 is 1. Well, that's kind of cool. We got a length of 1. All that work for 1. Whew. Seems kind of freaky, doesn't it, when you think about that? It's 1. All right, fine. Okay, yeah, that one works out nice. Where did this go? Oh, there it is. Okay, so the answer is 1. Hello, 1. Okay, and then the asteroid problem. All right, so we're going to take a look at something new. Let's see, I think I said before, we are officially a day behind the schedule I posted before. And as of today, we are officially a day and a half behind. That's okay. I'm going to introduce the next topic, which is areas of surfaces of revolution. And these are a cross between arc length and volumes of revolution. So we know how to revolve things in a couple of ways using washers or using shells to generate a three-dimensional object. And we looked at how much volume was inside those. Now we're going to look at what's the surface area like. And it turns out it's not too bad. So just a couple of brief introductions to that. If you just think about a cylinder, when we unwrap a cylinder, we just basically have like a sheet of paper. Okay, and we've looked at that idea before. Let's suppose this right there is my delta x, and then I have some radius here, we'll call that y. This circumference here unwrapped to be that length over there. Circumference is 2 times pi times the radius. And the width of this thing is delta x. Now, it turns out to find 3D revolved surfaces, you need more than just a cylinder. What you need are pieces of cones. Because if you think about the curves that we were playing with arc length, to find the arc length, I basically picked 2 points and then drew a straight line between those 2 points. And if I then, revolve that around an axis like the x-axis, I'm going to generate a piece of a cone, right? If you take a diagonal line, revolve it around an axis, you're going to generate part of a cone. So I'm going to generate something that looks like this. My dx here would be that horizontal distance. This diagonal, I'm just going to call that L for now. Unlike a cylinder, I'm going to have 2 radii. I'm going to have a little radii on this side. Let's call that y1. And I'm going to have a bigger radius on this side. Let's call that y2. That's not 1/2. That is a y2. If we unwrap that thing, we're going to get something that looks like this. It's like a teepee unrolled with a big opening at the top. And it turns out the surface area of that thing isn't too hard to find. It's pretty similar to the surface area of a cylinder. What you end up with is the area is equal to, where'd it go? 2 pi times the average of your radii. So y1 plus y2 over 2. And I didn't give myself enough room to write that down. Slide it over. Pen times the length of that diagonal. And those diagonals, again, those are what we were using for arc length. Remember yesterday? They come from the Pythagorean theorem. Okay, so in essence, if in this triangle right here, that's really a delta x and that's a delta y. Delta y. So according to the Pythagorean theorem, wouldn't L be the square root of delta x squared plus delta y squared? And what we're going to do is we're just going to have a whole bunch of these little line segments that revolve, and we're going to add them all up. Right, so we're going to end up with a Riemann sum again like we did yesterday. It's going to be a little more complicated Riemann sum because it's not just L like we were playing with yesterday. I get this extra baggage here to deal with. Okay. So what's going to happen is I want to have to add up all these little, they're called a chunk of a cone like that with the top chopped off is called a frustrum. Kind of a weird name. This sucker right here is a frustrum. Frustrum is just a cone with the top chopped off. That's all. All right. So what we get is we have our 2 pi, and we're going to get a whole bunch of them. So I'm going to have, let's call it a yi plus a yi minus 1. Right. So the y value right before it over 2. I've got to average those things. And L is the square root of delta x sub I. Ooh, that does not look like a delta. Looks like an A. Delta x sub I squared plus delta y sub I squared. That's if I partition up the x-axis into little chunks. And we want to add all of those chunks up as I goes from 1 to whatever n is. So that's numerically how to calculate it. So we could take any curve, that's the Riemann sum, to revolve that curve and figure out its area approximately. Well, what do we do with Riemann sums once we have one set up? We take the limit as n goes to infinity. So we want to take the limit as n goes to infinity of this whole thing there and see what happens. Okay, so what's going to happen there? Well, in the limit, as n gets bigger, all these yi's and xi's are getting closer and closer and closer to each other. Okay. So we got that 2 pi just chilling out. The limit of a sum is an integral. The 2 pi is hanging out. These two y values essentially become the same number. They get merged on top of each other. So we're going to get a y plus y over 2. What happened to this? Do you remember how we did a little algebra on that and it turned into something funky? What did that square root turn into when we did arc length? It turned into the 4th step in our 5-step process for finding arc length. It turned into the square root of 1 plus y prime squared is what it turned into. Remember we did that little jiggery pokery by dividing this sucker by delta x over delta x. And so we're going to end up with a delta x at the end here outside of the square root. And then starting at some x value a, ending at some x value b. Okay, we still got a little more cleanup to do here. Back to my picture here, this blue curve here, I have blue, y is some function of x, right, on the blue curve. So we're just going to replace y with f of x and clean it up a bit. Let's see, what's y plus y? Well, that's 2y divided by 2 is just y. Okay, so in the end here, I'm going to have the integral as x goes from a to b of 2 pi. Instead of calling it y, I'm going to call it f of x. It's the function we are rotating times the square root of 1 plus f prime of x squared with respect to x. So it's kind of like finding arc length, but since we're revolving it, we get this 2 pi y as a multiple. Sometimes that makes things better when we're trying to find an antiderivative. Sometimes it makes it way worse. So just like with arc length, sometimes we just got to throw up our hands and whip out a computer and say, just give me an approximation. Oh, 13.61, thank you. That will do. Other times we're able to algebraically manipulate this mess and find an antiderivative. But just like with arc length, because this algebraically is so complicated, we really should apply a step-by-step process. And so just like with arc length, step 1 is to find the derivative. Step 2 is to square it. Add 1. See if you can clean up that square root. See what happens then when you multiply back by the original function. So we're going to have a 6th step in there. So we're out of time to actually do one of these today. I posted homework. I don't know if anybody noticed, I tightened up the due dates. About half of the class hasn't been doing homework in a timely manner, which is making me a little nervous. So I made the due dates a day earlier than I normally would. Usually if I cover a section, I make the due date the next night. I'm going to loosen that back up because people seem to be working harder again. Seems like after the test, people kind of relaxed a little last week, but we got lots of work to do. I'm going to move the deadline for tonight's homework to tomorrow. We'll do more arc length tomorrow, and then I'm going to give you an informal physics quiz tomorrow because the last 2 sections are about work and pressure. So I want to see what you guys know about work and pressure before we dive into it. All right. So that's it for now. Have fun, do good math, be careful. The roads are icy in a lot of places. And I'll talk to you soon. See you, Stanton. Have a good day. And stop.